Hello and welcome to this UmojaHack Africa 2022 Advanced Challenge. It's a challenge about African snake antivenom binding, and we are going to help researchers to find cross-reactive antibodies to this neglected tropical disease, which is the snake bite. This is a challenge co-organized with InstaDeep and the Technical University of Denmark, together with Professor Tim Jenkins. My name is Nicolas Lopez Carranza. I am the BioAI lead here at InstaDeep, and I am gonna happily be going through the notebook, the starter notebook for this challenge. We did put the notebook on a Google Colab that can run, and you can get a free GPUs, so it might be a useful solution for those who don't have access to compute. And we are going to be use a data set provided by DTU, and the data set stems from a high density peptide microarray experiment. And as I said, it's going to address how cross-reactive 8 different commercially available snake antivenoms are, and where in the toxin sequence, which forms the venom, these antibodies react into. So we have this score with this signal score that gives us an idea of where in the whole protein sequence the antibodies are most reactive. And what we are actually gonna have to predict is this signal. So this signal column, we are gonna use other columns in the dataset, like for example, the toxin chimer or the antivenom type. You're actually free to use any column that you want to actually predict how this signal coming from the high density peptide microarray experiment is gonna look like, okay? So for this, we are gonna first load libraries that we are gonna be use. This time we decided to use PyTorch to solve the challenge. I put it the two data sets, the train and the test data sets, on Google Bucket, so it's easy for you to download and to read. And let's have a look at how the data looks like. And we have a few columns. As I said, we have a column which is the unique identifier, which is actually the concatenation of the UniProt ID, the position start, and the antivenom, as you see here. And what is this UniProt ID? Well, this is a identifier based on UniProt database that, for example, let's take one example, this POC 6B4. When we look at it in UniProt, and you can do the same with any of these IDs, what you have is like a protein that it is this disintegrin subunit A, and the organism is the X, which is the soul-scaled viper snake. You can have more information about this particular snake, and I see some nasty image of this viper snake, which releases toxin, and this toxin contains proteins, and these proteins are the ones that we are looking at, and one of them is here. You can actually see what is the structure of this protein here in UniProt, and also you can like have a lot of other information. For example, the predictive structure from AlphaFold, which seems to have a high accuracy. So this protein is gonna be binding some receptors, yes, and this is how the toxin acts. And what we are gonna do is take pieces of these proteins, like of 16 amino acids, and this is what we call a chimer. And we are gonna see how these chimers react with some commercial antivenoms. And this is what the dataset is all about. So we have this UniProt ID, if you feel to take a look at it. Then we have the chimer position start, and this is the start position in the toxin global sequence, okay, the one in UniProt, and the chimer position end, which I said is this chimer is k equals 16, so it's a 16mer. And we also have the antivenom, which is in this case the bioclone, and the chimer, so the 16 amino acid sequence that are part of this larger sequence. and the value of signal, which is our actual value that we are going to predict. In this case, the signal is quite low. We want to, if we have cross-reactivity or reactivity, actually, we will expect a higher signal. Then we have the genus of the snake. We saw that UniProt and this genus matches, which is the Echis snake, the viper, and then some other protein families that you are welcome to have a look at on the data set. More of every column of the data set you can find here in the description. So for this particular challenge, we are going to build a model that is going to take into consideration the antivenom, okay, so it's a multi-class variable, the chimer, which is a sequence, and we are going to sequence of amino acid that we are going to treat with an LSTM, and the position, because maybe the position where this starts in the whole sequence has some sort of information. So we also will use the chimer position start column to predict the signal. So for this, the first thing we are going to do is create some maps, because neural networks cannot do well with just text data or sequence, so we need to convert our maps into actual numbers to be useful to crunch on these neural networks. And here we end up having the amino acid maps, which shows like each of the 20 amino acids possible. So you know that these proteins are all formed by 20 amino acids. We enumerate them, and these are the possibilities for the chimer sequence. So it can be one of these 20 amino acids. It will be conforming that sequence. And then the antivenom, we say we have some 1, 2, 3, 4, 5, 6, 7, 8 different antivenoms, and we also enumerate them to be able to input into these embedding layers. After we have these maps, we are going to use scikit-learn to split our trained data set into validation and a training set. Classic. And here we have the two sets, and the test set we are gonna use it as it is on the CSV, right? So we are not gonna do changes there. Then we are gonna have a look at if Colab gives us GPUs. In this case, I do not have a GPU because there was no GPUs available, but if you are lucky, you will get a GPU for free using Google Colab. And we are gonna convert these data frames into torch data sets, right? So essentially, we are gonna inherit from this dataset class, and we are gonna have to implement this getItem method that basically we will overwrite the base class. And we are gonna be supporting fetching a data sample for each given key. So this is how we will do it. And so let me execute this. And we are gonna instantiate the three datasets: the training, the validation dataset, and the test dataset that we are gonna be using later for training. Let's have a look at how this dataset looks. But essentially, the trained dataset has the chimer, which is a tensor representing the amino acid sequence of 16 amino acid, but in this case numerical values. The antivenom, which is a scalar representing one of the 8 antivenoms, and the positioned end and position start tensors. Then we will have to define a batch size and number of workers. And we are going to create what we call in PyTorch the data loaders. No, and the data loaders, what they are is they combine a data set and a sampler, and they provide an iterable over the data set. So when we are training, we can iterate through the data set and load it into the actual machine learning model. And after we have all these data loaders in place, we are going to be able to define the model that we are going to be using. And for this particular case, we are going to create a simple sequence model. I said we are going to be using by LSTM. So you see here that we have an embedding layer to input the chimer, so the amino acid sequence. Then we have another embedding layer for the antivenom, so this multi-class. And finally, third embedding layer for the position in this sequence. After this, we are going to have a linear layer, okay? And we are going to look at the architecture in more detail in the plot later. But here you see how we are going to be treating the sequence using an LSTM. Is your work to later convert this into maybe something more performant like a transformer. You could try different things, but actually let me have a look at the architecture here in more detail in the TensorFlow. We have the chimer, we crunch it through some LSTM layers, so sequential models, and then we will concatenate everything, put some linear layers. Let me zoom in here. Yeah, some linear layers, and then finally we will get our predictor, our output of the model, which is going to be the predicted signal. Yeah. So once we have the model defined, we are gonna create an instance of the model. But if you see, one of the things we need for instantiating this model is the maximum position. And like, what is the maximum position? Well, we can concatenate both data sets, the training and the test data set, and look at which is the maximum position in these data sets. And here is what we are doing. And this is the value that we are going to be using. So here we see, so here you will see that the maximum position start is 596, okay? So there is a sequence that has a chimer starting at position 596. So it's a long sequence, let's say probably more than 600 amino acids. And finally, we are going to instantiate our model, yes? And for the moment, we are, for the training, we are going to use 10 epochs. We are going to be using early stopping 5, and we are going to use this MSA loss function and an Adam optimizer. So everything very classic here. And we are going to look at the training loop. As I don't have GPUs, I will not launch the training at the moment, but you can try it if you get GPUs. And I did a training previously on this collab when I had a GPU available. And what you see is here that we are learning. We see like the loss function, like the loss diminishing, which is good. And we recorded the checkpoint. We saved the checkpoint after the training. Here you see the training, all of the 10 epochs that we decided, and then we save the model here in model.pth. Once we have the model saved, we are going to be able to run inference on that model on the test data set. For that, we define this predict test function. Yes, and here we are doing inference, although the inference is happening on CPUs. So it's gonna be a bit slow. Hopefully, guys, you're more lucky than me on getting a GPU instance from Collab. Now the inference has finished. So finally, we are gonna have a look at the signal distribution. So this is our target function distribution. Our target label distribution. And so here we have the predictive values coming from the inference. We see that the distributions are not quite similar, but we were going to compare with a random distribution, no? Like a random predictor. And let's see if at least we do better than just randomly guessing what is the signal. I hope we do. And for that, we are going to be using scikit-learn as well. And we see that for a random predictor, you have, for example, a mean absolute error of 1.6. Okay, regarding this LSTM model, we have a mean absolute error of 0.96. So we improve on both mean square error and root mean square error, and also mean absolute error. So that means that our LSTM model trained on 10 epochs works. So now the challenge is on you. Can you improve on this model? And what I'm curious to see what kind of solutions you are going to bring to this problem. Hope it is clear, and good luck for the challenge.